Hello, my name is Joshua Gaddis, and today I'm presenting my presentation, which is on fraud networks and banking systems. I am using a divide and conquer approach with dynamic programming for optimization. So every day, millions of digital transactions are made through banking systems. Among them, some are used by coordinated groups to cover up illegal activities. These activities often form fraud rings where money circulates through multiple accounts and eventually return to its origin. We are looking for these rings or cycles in the transaction data. Traditional systems rely on sequential transaction scanning or manual audits, but as these transaction networks grow, these methods fail to scale and brute force detection becomes obsolete. So just moving forward, this is just a kind of like an overview about the network and how things are doing. So we're using a directed graph. So each node is going to be represented as an account. Each account has a unique ID, name, balance, and time of creation. This is really important. Some fraudulent groups create new accounts to add more accounts to the pool, making it harder to track. Edges, they are used to track the amount of money that is sent from an account. And this graph is going to be referred to as a network. And this network links all the transactions together using edge list and adjacency matrix for faster computations. We could use this very exhausting DFS brute force method for this kind of more direct way to search for suspicious cycles in the transaction network. I did my best to optimize it. However, this still yields a time complexity of v to the cubic root. The network kind of relies on the recursion stack, which helps and acts as like a GPS to traverse the network. So basically, you just start at a root and you keep on going until you find a cycle. That cycle will get added to the recursive stack. And then this recursive stack kind of will say like, hey, okay, you're kind of going in a loop, time to move on. Without the recursive stack, you can easily get caught in a loop and you just have a really large, a pretty big problem, and you can't move on going forward. So we can easily improve this algorithm. So basically what we'll do is just use dynamic programming with divide and conquer. So the idea is to still use DFS for the divide and conquer part. However, we're going to sprinkle in some dynamic programming and store previous computed paths, kind of preventing these redundant calculations. I do have like a mini example here. We have a individual here named John, and he's caught in like this fraudulent cycle. So instead of looking at all of John's, like, where is he sending money to, like who's sending him money, we're just going to just focus on what John's sending out, and then using DFS, and then the dynamic programming is going to calculate who he's sending money to, which will help us, kind of say these values. So if he sends money to Alice and we see Alice is sending money back, we can store these values and we don't have to keep on doing it for every single transaction. So this main algorithm focuses on divide and conquer. As I said previously, we're going to be using DFS, and we're just going to traverse every single unvisited node and its descendants, and they will just all get added to the subnetwork. Each recursive call will get isolated into what I'm calling a fraud cluster. And then, so this conquer, this is kind of where dynamic programming will come up in this conquer. So we're using an algorithm called Tarjan's algorithm, and it just explores each of the like subnetworks that was created by the divide independently, and it computes the discover time and the low link value. We'll touch on those in a little bit. And then when this is done, we're going to combine it all together, and it will remove these what's called strongly connected components from the search space. So then we're not getting caught in like this loop. So it kind of cuts out the need for a recursion stack. Um, so the dynamic programming, as I said, it mainly falls in the conquering stage. So during the conquering stage, of the algorithm, dynamic programming is used to store the intermediate results and reusing the recursive calls over and over again. So without it, the dynamic programming, it's no better than the brute force approach, using a time complexity of v cubed. However, using dynamic programming, it drastically cuts this in half, or even more than half, and it leaves just a big O of v plus e, which does make this algorithm fast enough for real-time fraud detection. So we're going to apply all these techniques together. So we're going to divide the problem into sub networks, and then each of these sub networks are going to get added into like their own neighborhood. And then we're going to conquer that. So we're going to use DFS to find all the reachable accounts. Using dynamic programming, we're going to record the lowest reachable discovery index for each node. And then we're going to combine all these results together. So if multiple nodes have the same root, they're going to belong to the same strongly connected component, or the SCC. We're going to mark this SCC as potentially fraudulent, and then a representative can check out this fraud cycle and to see if it's actually fraud. In the conquer stage, we're just kind of like using dynamic programming to optimize this. So we're just kind of finding and saying like, hey, this is the lowest, or the lowest minimum node that we computed, and then this ensures that we're not doing any redundant traversal or reprocessing. And then I added kind of this in. It's just going to print this out, and the idea is that it's going to flag every account that's involved with this cycle as fraudulent. So maybe if we implement this out completely, it will not allow them to send any more money or something like that. So here's a little bit of the pseudocode for this. The time complexity for this, DFS traversal, we have a time complexity of big O of E. Edge exploration, we have a time complexity of just E. And thanks to dynamic programming, the low link update has a time complexity of just 1. So this gives us a final time complexity of big O of V plus E. So in this pseudocode here, we have our like first line, which is just our procedure or function. And then we're going to set our global time to 0, which just initializes the process, ensures every node is visited. It just kind of starts as like a counter used for discovery time map for each vertex, representing the order in which the nodes were like visited. And then we're just kind of going to like loop over every vertex in the graph, because the graph may not be fully connected. So you can have, for example, a group of people that are sending money to each other that know each other, and then you have another group of people that know each other and sending money to each other, but there's no connection in between them. And then we're calling this strong connect thing here. So if something hasn't been discovered, we're going to call this strong connect, and we're going to explore all the neighbors of V. And this is what this one does. Like at its core, it's the Tarjan's algorithm, and it performs a DFS it performs like a DFS algorithm, and it tracks connections using two arrays. And these are the two arrays here. Moving on, we're just going to compare the brute force. So the brute force just fails in comparison to this. Just even though it's like dead simple, just conceptually, it's not practical with a dynamic and ever-growing graph. So the Tarjan's algorithm using dynamic programming just completely speeds it up and just puts it into linear time. Although there's a slight trade-off using more space because you're not using a recursive stack at that point. The gain of the speed is more ideal for these large transaction networks. Sources here, this is the paper that Tarjan published. I also looked up Geeks for Geeks. This is just something to help me better understand this very complex and very detailed paper. And I don't want to butcher his name, but William Fiestet, he had a YouTube video that I watched that actually introduced me to this concept. And of course, I have my source code here. So we're going to do a quick live demo of this. So I'm just going to do my NeoVim, and then we're just going to open it up. As you see, like here's the struts and everything that we saw before. We can kind of go in, and then we can see like here are the functions. They're very basic functions, like the print functions, and then these are the two functions that I used in the pseudocode, which detect. This is the DFS, and then this is the I believe the strong connect here. Yes, the strong connect, and then the last one there is the Tarjan SCC. So let's run it. I'm using my own kind of project manager that I made for C. So I'm just going to run this, and as you see, we have 10 accounts here. With different balances, and the time isn't really utilized here because I am using the time standard library, so it's just creating all these transactions at the same time. I didn't really figure out a way to kind of space it out without making it all static. I did want it kind of dynamic, like that. So, but as you see, like we have the adjacency matrix here, which is used to kind of backtrack and then go through. Backtrack's probably not the right word for that, but we use the adjacency matrix for the dynamic programming. And as you see, the cycles were found. So 5 and 6 here, which is these accounts, Frank and Grace, they got caught cycling money. And then we have another case of fraud with 7, 8, 9 here with 7, 8, and then 9. Heidi, Ivan, and Judy. As you see the transactions, these transactions check out here, but then once you get around here, you're seeing some like loops and stuff like that, and it did get picked up. So this is my implementation of the Tarjan's algorithm, and this is my project on fraud cycles and banking networks. Thank you so much.